Avogadros Law talks about the relationship between the amount of gas that's in a gas sample and the volume of the gas sample. So what does that mean? Well, first of all, a gas sample is just a fancy term that means a bunch of gas we have anywhere. So for example, this balloon has a whole bunch of gas in it that is what's keeping it inflated. So the gas in here can be considered a gas sample. This gas sample, the balloon, has both a volume. It takes up a certain amount of space that we could measure, and there's also a certain amount of gas inside. When I talk about the relationship between these two things, all I mean is what happens when I change one of them, what happens to the other? So let's talk about this. Let's imagine that I have my balloon and investigate the relationship between these two variables, okay? Here is a real quick drawing of the balloon, okay? So talk about the relationship here. Let's say that I untie the knot at the end of the balloon and I blow more air into it. That is going to increase the amount of gas that's in that balloon. So we'll say that little n, the symbol that we use to indicate the amount of gas, little n goes up. So the relationship, what effect is that change going to have on the volume of the balloon? Well, okay, this isn't exactly rocket science. It's going to make the volume of the balloon get bigger. We increase the amount of air, the amount of gas that's inside, the volume goes up. So N goes up and V goes up as well, okay? Let's look at the opposite case. I untie the knot at the end of the balloon and I let a whole bunch of gas out. So in that case, little n is going to get smaller. And what effect is that going to have on the balloon, on the volume of the balloon? Well, the balloon is going to shrink. It's going to take up less and less volume. And here's our baby little balloon here. So the volume has gone down. So here's a relationship. When one of them goes up, the other goes up. When one of them goes down, the other goes down. What's this kind of a relationship called? You may already know. This is what we call a direct relationship. It's when two variables move in the same direction. And we can show this relationship with a graph here. Here on the x-axis, I have the amount of gas, which is in moles. We'll talk about that later, but that's usually how we measure the amount of gas in something. Amount of gas here, and on the y-axis, I have volume. As we increase the amount of gas, the volume goes up as well. And it actually turns out that if we double the amount of gas that's in a gas sample, like a balloon, it also doubles the volume, the amount of space that that gas sample takes up. So here's a graph of Avogadros Law. Okay, now one thing is important to keep in mind, and that's that when I was talking about the balloon, I was changing only two things, right? The two things I was changing was the amount of gas, that was one of them, and the volume was the other. There are other things that I was not changing about that balloon, okay? While I was changing the amount of gas, I was not changing the temperature. Okay, it's not like I was letting out gas and I was heating up the balloon. You can't do that. The other thing that I wasn't changing is I wasn't changing the pressure. So it's not like I was blowing up the balloon, but then taking it up to the top of Mount Kilimanjaro, where the air pressure is much less than it is here down at sea level. So I was also not changing the pressure. So when we're talking about Avogadros Law, the relationship between the amount of gas and the volume, I can change either one of those, but I cannot change the pressure or the temperature of that gas. These are my constants. These are my variables, okay? There's one thing that I want to show you really quickly, okay? And that is this device that we talk about a lot when we're doing Avogadros Law, okay? You always see pictures of this when in textbooks and stuff when we're talking about Avogadros Law, so that's just why I want to talk about it for a minute. And this is a crazy thing, okay? It's a canister of gas that has a sliding top. And I made one, well, I made a model of one out of a soda bottle. Okay? And you can kind of see how this works. That I have, imagine that this is a canister that holds gas and I got a pipe that goes in that I can add gas into. And then you can see this top. Imagine that this top could slide up and down in here. Okay, so what's the point of this? The reason we always see these guys, and this is usually how they're drawn when we're talking about Avogadros Law, is because they're a way to change the volume of a sample of gas without changing its pressure. This pipe here indicates something that I could use to pump gas in. So imagine that I pump gas in here. That would normally raise the pressure of a container, but not if the top can slide. Instead, the volume changes. I add a little gas in here, and the top slides up. And then I suck a little gas out, and the top falls back down. Instead of the pressure changing, the top slides up and down. So that's why you always see pictures of this kind of an apparatus, this kind of a device. That's a fancy word, apparatus. But the point of it is just that it's a canister of gas with a slidable top that can go up and down, that can change the volume of the canister as I change the amount of gas that's in here without changing the pressure. Okay? So, Avogadro's law is used a lot for math problems. And when we talk about math problems with Avogadro's law, the form of the law that we usually use is N1 divided by V1 equals N2 divided by V2. This equation assumes that some sort of change has taken place, like the change I was talking about earlier. It assumes that I have an initial amount of gas and an initial volume, that's before the change, and then the amount of gas and the volume change after I do something to it. Okay? So, let's work through this Avogadro's law by looking at a math problem here. So, in a sample of gas, 50.0 grams of oxygen gas take up 48 liters of volume. Keeping the pressure constant, remember that's important in Avogadro's law, pressure's got to be constant. Keeping the pressure constant, the amount of gas is changed until the volume is 79 liters. How many grams of gas are now in the container? When I'm doing problems like this, I find it really helpful to keep track of my variables by making a chart like this. I've got my before and I got my after, because we said there's a change that takes place, this little arrow, we're moving from one to the other. Let's get our variables straight before we plug anything into this equation. So, in a sample of gas, 50 grams take up 40 liters. That's what we start with, okay? So that means that N1, I'm going to make that 50.0 grams, that's that. And the volume, it says here that they take up 48 liters of volume, okay? So 48 liters is before the change. Now here's the change. Keeping the pressure constant, the amount of gas is changed until the volume is 79 liters. Okay, so that means that my V2 is going to be 79 liters, the volume after the change. And the question asks, how many grams of gas are now in the container after the change? So it's going to be N2 that I'm going to be solving for. So now I got my variables straight. I know what I'm going to be solving for, and I know the other guys. Okay. Now it's important to look at units. There are two things to keep in mind. When we're doing Avogadro's law, this little n always has to be in moles, okay? Moles is usually how we keep track of the amount of gas we have in a sample. So the amount of gas here was given in grams. That's not going to work. We're going to have to convert it to moles. And this is probably the biggest mistake that people make when they're doing Avogadro's law. They don't remember to convert grams into moles. So hey, if you get a practice problem and your N1 or N2 is already in moles, you're all set. No big deal. You can skip this step. But if you get a practice problem like most of them are, where the N's are in grams, we're going to have to convert it to moles. So we'll do that in a minute. The other thing is the V's. It doesn't matter what units the volume is in, as long as they are both in the same units. Okay, so liters here, we're set. If this was milliliters, milliliters, that would also be okay. But it wouldn't work if one was milliliters and the other was liters. Okay, so volume units don't matter as long as they're both the same. Okay, so now I've got my before and I've got my after. I'm going to change my 50 grams into moles. And in order to do that, I'm going to have to use the molar mass, which tells us how much 1 mole of a gas weighs, okay? So the molar mass for oxygen is 2 times 16 because each oxygen atom weighs 16, and then we do 2 times that because there are 2 oxygens, and we get 32.0 grams per mole, okay? So now we want to go from grams, which is 50.0 grams, and I want to multiply this by this grams per mole fraction in a way that's going to cancel out grams. So I'm actually going to want to flip this so that I have grams on the bottom so that they cancel out, okay? So I'm going to do 1 mole divided by 32.0 grams. All I've done is flip this. Now I have grams up here and grams down here. That means they cancel out. I'm going to be left with moles, and the answer that I get there is 1.6 moles. So I can cross out my 50 grams and replace it with 1.6 moles. Now, I got my n's in moles. Well, I got one of my n's in moles. I got both my volumes in liters, which is the same unit, and now I'm ready to go. So it's going to be N2 that I want to solve for. I want to rearrange the equation to get N2 by itself on one side of the equation. So to get N2 by itself, I want to get rid of the V2 that's in the denominator right now. So I'm going to multiply both sides of the equation by V2. Now I have V2 above V2 down here, which means they cancel out, and I'm going to be left with V2 times N1 divided by V1 equals N2. Some people like having the variable that we're solving for on the left, so I'm just going to switch that real fast, but it doesn't make a difference. I'm just going to put it in reverse here, V2 times N1 divided by V1, okay? Now we're ready to take our variables that we've laid out here and plug them in. So I've got N2 equals V2, 79 liters, times N1, 1.6 moles, divided by V1, which is 48 liters. And when I do that, the number that I get is going to be, let me check here, 2.6. And what are my units going to be? Well, liters up here, liters down there cancel out. So my final answer here is going to be 2.6 moles. I'm not quite done with the problem yet, though, because my question here asked me how many grams of gas are now in the container, not how many moles of gas. So now I'm going to have to take this mole number and convert it back into grams. How am I going to do that? Well, what I'm going to want to do is I'm going to want to take the molar mass of oxygen again, which, as we said earlier, was 32.0 grams per mole. And I'm going to take my mole number, 2.6 moles, and I want to multiply it by this conversion factor in a way that's going to get rid of my moles. So I can keep the conversion factor just as it is right now, and I'll have moles on the top, moles on the bottom. So 2.6 moles times 32.0 grams divided by 1 mole. Now mole on top, mole on the bottom, they cancel out. And when I do the math, 2.6 times 32, I'm going to get 83 grams, which I'm going to round to 2 significant figures because I have 2 sig figs here and 3 sig figs here. I always go with a smaller number. So I am going to get 83 grams as my final answer. Okay, so that's Avogadro's law. If you have questions on how to rearrange this law to solve for any of the other variables, I've done a video on that. Check out my rearranging gas equations videos. If you have any questions in general about these gas laws, be sure to check out the gas laws extra help and frequently asked question video, which should clear up any other questions that you have with this sort of stuff.